Welcome to today's paper reading. Today's paper is titled, RouteLLM, Learning to Route LLMs with Preference Data. This paper, titled RouteLLM, Learning to Route LLMs with Preference Data, was authored by Isaac Ong and colleagues from UC Berkeley, Scale, and Canva. It is currently under review as a preprint. The abstract discusses the trade-offs involved in choosing large language models, LLMs, where more powerful models offer better performance but at a higher cost, while less capable models are more economical. To tackle this issue, the authors propose efficient router models that dynamically select between a stronger and a weaker LLM during inference to optimize the balance between cost and response quality. These routers are trained using a framework that leverages human preference data and data augmentation techniques to enhance their performance. Evaluations on recognized benchmarks indicate that this approach can significantly reduce costs, up to 2 times in some cases, without compromising the quality of responses. Additionally, the router models exhibit strong transfer learning capabilities, maintaining performance even when the underlying strong and weak models are changed at test time. This suggests that these routers could offer a cost-effective, high-performance solution for deploying LLMs. Recent advancements in large language models, LLMs, have shown significant capabilities across various natural language tasks. These models have been enhanced by architectural innovations like the transformer and improvements in data and training infrastructure. However, LLMs vary widely in terms of cost, size, and the data they are trained on, leading to differences in their capabilities. This variability creates a challenge in deploying LLMs practically, as routing queries to the most capable models can be expensive, while using smaller models may compromise response quality. To address this, LLM routing aims to optimize the quality of responses within a given cost by intelligently routing queries to the most appropriate model. This involves a router model that can infer the intent and complexity of queries and adapt to the evolving landscape of LLMs. Figure 1 illustrates the trade-off between performance and cost in routing large language models, LLMs, such as GPT-4 and Mistral 8x7b. On the left, it showcases several routing models that surpass a random baseline and out-of-domain (OD) evaluations on GSM-8K. In the center, it highlights the enhancement in router performance through data augmentation techniques on MT-Bench. On the right, it presents the key metrics considered: call performance threshold, CPT, shown in green, and average performance gain recovered, APGR, represented by the blue shaded region. These metrics help in understanding the balance between cost efficiency and response quality in LLM routing. The routing function R is designed to map a query to an answer by selecting the optimal model from a set of n models. This function acts as an n-way classifier, determining which model should respond to a given query. The challenge lies in balancing response quality with cost efficiency. In this work, the focus is on binary routing between strong and weak models. Strong models, like GPT-4, offer high quality but at a higher cost, while weak models, such as Mistral 8x7b, provide lower quality at a reduced cost. The routing decision is influenced by a cost threshold alpha, which controls the trade-off between quality and cost. To evaluate the effectiveness of the routing function, metrics such as cost efficiency, average response quality, and performance gain relative to the performance gap between models are used. These metrics help in assessing how well the routing function recovers the performance gap under various cost constraints. The methodology begins with the collection of preference data from 80,000 battles on the Chatbot Arena platform. This data, denoted as DARINA, includes user queries, model responses, and human judgment labels. However, the raw data suffers from label sparsity, with less than 0.1% of comparisons between any 2 models. To address this, the authors cluster models into 10 tiers based on ELO scores and derive preference data for training. They also employ data augmentation techniques, including golden-labeled datasets from benchmarks like MLU and LLM judge-labeled datasets using GPT-4, which significantly reduce costs. The routing approaches explored include similarity-weighted ranking using a Bradley-Terry model, matrix factorization to capture low-rank structures, and classifiers using BERT and causal LLMs like Llama 3B. These methods aim to predict the winning model for a given query based on the preference data. In this section, we discuss the experimental setup and results. The training data consists of 65,000 pairwise comparisons between 64 different models, predominantly in English. The evaluation benchmarks include MMLU, MT-Bench, and GSM-8K, with a focus on out-of-domain generalization. For the routers, we use OpenAI's Text Embedding 3 Small for embedding input queries and perform full parameter fine-tuning on BERT and Causal LLM. Representative models for evaluation are GPT-4-1106 Preview and Mixtral 8x7b. Table 1 presents the performance metrics of various routers on the MT-Bench evaluation. The routers are evaluated based on their call performance threshold, CPT, at 50% and 80%, and their average performance gain rate, APGR. Notably, the CPT, 50%, score achieved by the routers is 95% of the performance of GPT-4. The matrix factorization router stands out by requiring only half the number of calls to GPT-4 compared to a random router to achieve a PGR of 50%. Additionally, augmenting the training dataset with Judge leads to significant improvements in APGR, with the BERT classifier showing an increase of over 50% compared to the random baseline. This table highlights the effectiveness of the routers in reducing costs while maintaining high performance on the MT-Bench. Table 2 presents the 5-shot MMLU results for our routers. Notably, the CPT, 50%, score for our routers is 92% of GPT-4's performance. Routers trained solely on the Darina dataset exhibit poor performance due to most MMLU questions being out of distribution. However, augmenting the dataset with Gold significantly enhances router performance, demonstrating the effectiveness of dataset augmentation even with a small number of additional samples. Table 3 presents the 8-shot GSM-8K results, highlighting that the CPT, 50%, score of 75 is 87% of GPT-4's performance at 86. Routers trained solely on the Darina dataset exhibit poor performance due to out-of-distribution questions. However, significant improvements are observed when the dataset is augmented with Judge data. Notably, the Causal LLM classifier outperforms other routers, requiring 17% fewer GPT-4 calls to achieve CPT, 50%, and CPT, 80%. Table 4 presents benchmark dataset similarity scores, showing a strong correlation between these scores and the performance of routers on corresponding benchmarks. This correlation provides a quantitative method for improving router performance. Dataset augmentation, whether using golden-labeled or LLM judge-labeled datasets, shifts the preference data distribution to align more closely with benchmarks, thereby increasing the similarity score and translating into performance improvements. Higher similarity scores are associated with stronger router performance on specific benchmarks, as highlighted in section 4.1. This metric is also valuable for understanding the relative performance of routers across different benchmarks, such as the ARENA dataset's higher similarity score with MT-Bench compared to GSM-8K and MMLU, which explains the stronger router performance on MT-Bench. Table 5 presents the MT-Bench results for the model pair Claude 3 Opus and Llama 3 8B. The data demonstrates that our routers can effectively generalize across different strong and weak model pairs without requiring any retraining. The performance of these routers is comparable to that observed with the original model pair. Notably, the routers require up to 30% fewer GPT-4 calls than random selection to achieve comparable performance thresholds, indicating that the routers have learned common problem characteristics that distinguish between strong and weak models. Table 6 highlights the cost-saving ratios of our top-performing routers compared to GPT-4. Our routers achieve significant cost reductions while preserving the quality of GPT-4 responses. The dominant factor in our analysis is the cost of GPT-4 calls, and our routers can reduce this cost by up to 3.66 times. This demonstrates the effectiveness of routing and lowering expenses without compromising on response quality. Table 7 presents the cost and inference overhead of various routers, highlighting their efficiency in supporting real-world workloads despite the minimal additional costs compared to LLM generation. Key metrics include the costs per million requests, which ranges from $37.36 for SW ranking to $1.42 for matrix factorization, and the requests per second, with SW ranking at 2.9 and matrix factorization at 155.16. Additionally, the hourly cost of virtual machines for these routers is noted, with SW ranking at 39 cents and matrix factorization at 80 cents. In this study, the authors demonstrate robust routing performance across various benchmarks, including open-ended question answering, humanities, and math problems. By intelligently routing queries between a strong and a weak model, the routers achieve significant cost savings while maintaining high response quality. The results also emphasize the effectiveness of dataset augmentation in enhancing router performance. For instance, training routers solely on the ARENA dataset leads to poor performance on MMLU and GSM 8K, but augmenting the training data with an LLM judge or in-domain data allows the routers to surpass the random baseline across all benchmarks. The largest performance gains are observed when the training data closely matches the evaluation data, as indicated by the benchmark dataset similarity score. The authors suggest that this framework offers a clear and scalable approach to improving routing performance for specific use cases. However, the study acknowledges a few limitations. Although evaluated on diverse benchmarks, real-world applications may exhibit distributions that differ substantially from these benchmarks. The authors propose that collecting a small amount of in-domain data can improve performance for specific use cases through dataset augmentation. Additionally, while focusing on the two-model routing setting, extending this work to multiple models is identified as a promising future direction. Finally, the study notes variability in performance among routers trained on the same dataset, which warrants further investigation. Thank you for watching.